Methods for linear systems, and in this video we will be talking about linear systems in normal form. So we say that a system of n linear differential equations can be represented or expressed in this form. Of course, here we have our unknown vector, so we say that x of t, and that is a column vector, and of course we have x1 of t, x2 of t, to xn of t. We also have a column vector for our f of t, and we will have f1 of t, f2 of t, fn of t. And then we also have a of t here as a vector with I rows and j columns, and that's a matrix, not a vector. And that's an n by n matrix. Okay, so the system is called homogeneous when f of t is identically equal to 0. You want to recall that an nth order linear differential equation written like this, and we had our n minus 1 p functions of t, just going to move that over just a touch so you can see that p to the n minus 1. We wrote this first order system in normal form, and we substituted x1 of t for y of t, x2 of t for y prime of t, and so on and so forth. So we did this by letting x1 of t equal y of t, x2 of t equal to y prime of t, and so on all the way to xn of t, and that was the n minus 1th derivative of t. So that is equivalent to this equation above when we make that substitution. And then that's how we come up with our matrix A of t. We have these p functions as that lower row. Let's go ahead and try our first example. Write the given system in the matrix form. X prime of t equals ax plus f. So we're going to go ahead and define our vectors. And we will have x of t equal to x of t, y of t, and z of t. And therefore, of course, we will have x prime of t equal to x prime of t, y prime of t, and z prime of t. And then we can take a look at this system over here. and see that f of t, we're going to have t 5 and the opposite of e to the t. And, of course, our matrix A. And we will have t squared, -1, -1, 0, 0, e to the t, t, -1, and 3. So there we have our 3 by 3 matrix. So this system becomes a matrix differential equation, and we write it just like this. So we have there's our matrix A. Here's our x vector. Of course, you could verify that this equation is equivalent to this original system by performing matrix multiplication and addition. Let's go ahead and look at our next example. Rewrite the scalar equation as a first-order system in normal form and express the system in the matrix form x prime a equals ax plus f. So in this system, we can make the following substitutions. We can say that x1 of t is equal to y of t, x2 of t is equal to y prime of t. And so with these substitutions, we can have now x1 prime of t is equal to 0 x1 of t plus x2 of t. And we have x2 prime of t equal to 10 x1 of t plus 3 x2 of t. And of course, we have our sine of t term. So we can now let x of t vector x of t be x1 of t, x2 of t, and that means that x prime of t is equal to x1 prime of t, x2 prime of t, that vector, and our matrix A is going to be a 2 by 2 matrix, 0, 1, and 10, 3. Okay, so with that, our system in normal form can now be written as here's our matrix A. Here's our vector of unknown functions. And here is our f of t vector. Okay, let's take a look at the next example. Write the system as a set of scalar equations. So now we're doing the opposite of what we just did. So what we can say is that we are going to let x of t equal x1 of t, x2 of t, and x3 of t vector. And now we can say that and here we have our matrix. And then here we have our vector of unknown functions. And here is our f of t. And you can see where we have created those vectors. And so now we can write our system as a set of scalar equations by saying that x1 prime of t is equal to x1 of t plus x3 of t plus e to the t. Likewise, x2 prime of t is equal to the opposite of x1 of t plus 2 x2 of t plus 5 x3 of t plus t. And x3 prime of t is going to be equal to 5 2 of t plus x3 of t. Let's take a look at this existence and uniqueness theorem. So if our matrix A of t and f of t are continuous in an open interval I that contains the point t naught, then for any choice of the initial vector x naught, there exists a unique solution x of t, that's our solution vector, of the whole interval I to this IVP. Before we go over this linear dependence of vector functions, I did want to talk about this linear operator. So we define this linear operator as L of x is equal to x prime minus ax. And of course, if our system is written as x prime minus ax equals f, and then we define this operator as L of x. So then now we can express this system in operator form. So then we can now express our system as L. So that operator on that matrix is equal to f. So basically the operator L maps vector functions into vector functions. So L is a linear operator, and for any scalars a and b and differential vector functions x and y, we now have this equation. So the linear operator on matrix AX plus BY is equal to A multiplied by the linear operator of X plus B, our scalar, multiplied by the linear operator of Y. As a consequence of the linearity of our operator, if we have our solutions to the homogeneous system X prime, and if we have them in operator notation, any linear combination of these vectors is also a solution. So with that, we can now go to linear dependence of vector functions. So the M vector functions are said to be linearly dependent on an interval I if there exists a constant, if there exists constant C1 dot 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 to Cm, not all zero, such that this linear combination is equal to 0. If the vectors are not linearly independent, then they are said to be linearly independent on that interval. So let's go ahead and take an example here. Determine whether the given function is linearly dependent or linearly independent, and we'll denote those with Li and Ld on the interval negative infinity to infinity. So we assume for all t, element of negative infinity to infinity, we assume that C1 multiplied by the vector T3 plus C2 multiplied by our vector 4, 1 is equal to 0, 0. So with that, we can say that C1T plus 4C2 is equal to 0, and 3C1 plus C2 is equal to 0. Well, the result of this first equation, this implies that C1 and C2 are both equal to 0. So, therefore, the given vector functions are linearly independent by our theorem. Let's take a look at the next example. Determine whether the given vector function is linearly dependent or linearly independent on the interval negative infinity to infinity. Here we notice that vector, the second vector, we'll call this x2 of t, actually, let's just go ahead and say we notice that this second vector is negative 3 times the first vector. So basically we're saying that negative 3 multiplied by this vector plus this vector could just say that these are equal. Therefore, the vector function is linearly dependent. Okay, we have defined our linear operator. Let's revisit Wronskian. So the Wronskian of n vector functions, x1 of t, x2 of t, all the way to xn of t, these column vectors are defined like this. The Wronskian of n vector functions is equal to the determinant of this matrix here. And you can see this is x 1 of t, and you can notice the notation all the way to xn of t. Let's go ahead and try to compute the Wronskian of these vector functions. Okay, so here we have in part A, we have the Wronskian have cosine of t, sine of t, cosine of t. And then, of course, we have that that's equal to cosine of t and then alternating, but now we are going to have 0. Whoops, we're not going to have 0 there yet. Plus okay, and we can clearly see that it is just going to be equal to that first cosine of t multiplied by, I want to do that, and that's equal to the cosine of t multiplied by cosine squared t minus sine t cosine t. Of course, then we end up with the cosine cubed of t minus sine t cosine squared of t. And I just factored a cosine squared, and I ended up with cosine of t minus sine of t. Okay, let's look at part B. Are these vector functions linearly independent on negative infinity to infinity? Yes, as you can see, these are independent on negative infinity to infinity. They are independent as vector functions. Is there a first-order homogeneous linear system for which these functions are solutions? Now, these cannot be solutions to a first-order linear system, since the Wronskian of solutions to a first-order linear system either never vanishes or vanishes identically. These, however, are solutions to the second-order system. Let's just take a look at that and see here that these are solutions to the second order system x double prime plus x equal to 0. So this is no, because there is not a first order system, since the Wronskian of solutions to a first order system either never vanishes or it vanishes identically. Okay, how are we going to represent these solutions in the homogeneous case? As you can see, we have f of t equal to 0. And we have an n by n matrix, of course, for our a of t, and it's continuous on that interval. So every solution to this system can be written as in this form. And of course, we have C1 through Cn as constants. Now let's talk about what a fundamental matrix is. We have a set of solutions where that are linearly independent on our interval I, and their Wronskian does not vanish on that interval. This is called a fundamental solution set. And so here we have this matrix. We have taken the vectors in the fundamental solution set and let them form columns of the matrix. So this fundamental matrix is where we have taken the vectors in our fundamental solution set. And these are the columns of this matrix. And you can see them right here. Okay, so if we have x of p is a particular solution to the non-homogeneous system shown here, so this is our non-homogeneous case, then every solution can be expressed in this form. So how are we going to solve these normal systems? We're going to first determine a general solution to the system. Then we're going to find a fundamental solution set. And those are our n linearly independent solutions to the homogeneous system. Then we will form our linear combination as we talked about above. Then we will find our general solution to the non-homogeneous system, and we find our particular solutions from there. Let's go ahead and take a look at this example. So here are vector functions that were given as solutions to our system here. And we want to determine whether they form a fundamental solution set. So if they do, we are going to then find the fundamental matrix for the system, and we will give a general solution. In order to determine whether they are linearly independent, we need to calculate their Wronskian. So let's go ahead and do that. So we have that the Wronskian made up of that matrix of vectors of t is equal to and we can see that that's equal to and go ahead and in working that out, you can see we have 0 plus e to the 4t here. Then, of course, we have minus e to the t, and we'll have 4e to the 2t minus a minus, so we have a plus e to the 2t plus e to the 3t, and we'll have 2 minus 0. And we actually, I'll go ahead and write it on this line. This is equal to, I'll just continue this next line. So here we have e to the 3t minus 4e to the 3t. You can see that we have negative 2e to the 3t, and this is not equal to 0. So of course, in this case, these vectors are linearly independent. So we do have a fundamental solution set to form. So our fundamental matrix of course we have x of t, it's a little bit big, And then our general solution of our system we can say is that x of t is equal to x of t, and there's our constant vector c is equal to c1 plus c2 times our second vector plus c3 multiplied by our third vector. So that is our general solution. Okay, let's look at our next example. Go ahead and first show this here, that this determinant of our second order determinant, we will get the following. So we have t squared. I'll just go ahead and work off of that. So we are just finding that determinant. And as you can see, this is equal to 0. So now let's assume that for some constants, C1 and C2, that's C1 multiplied by this vector plus C2 multiplied by our second vector is equal to our vector of zeros. Well, this implies that C1t squared plus C2t, absolute value of t is equal to 0, and C1 multiplied by C2 plus C2 multiplied by 2 times the absolute value of t is equal to 0. However, if we let t equal to 1 and t equal to -1, what we arrive at is, so let's say we take t equal to 1 and t equal to -1, we come up with C1 plus C2 equals 0. And then if t equal to -1, C1 minus C2 equal to 0. So therefore the system only has the trivial solution. Of course, when they are both equal to 0. Therefore, the vectors are linearly independent. And that concludes this video.